Okay, hi everyone. Welcome to another episode of Q&A on history of science and technology. So I see there are a bunch of questions here that were left over from last time. There was one here from Pavel, interested in the evolution of mechanics from Newton through D'Alembert to Lagrange and so on. I have to admit, I don't know that history as well as I might, but let me tell you some things I do know about the history of mechanics. So, I mean, the first question about mechanics is to get even the basics of how mechanical processes work right. So, for example, Aristotle, who wrote about many things, I mean, Aristotle was a huge maker of lists of things, animals, forms of argumentation that turned into logic. Also, kind of things that are sort of obvious about the world but should be written down, like what is the way that things determine how they should move. And so he had this idea. Oh, I realized something. I'm sorry, I just realized a mistake here, which I need to fix. Hold on one second. Okay. In any case, okay, about Aristotle. So there were sort of questions about what was the basic origin of motion? How did motion work? That was a thing that was thought about in Greek times. It's really very unobvious what motion actually is. When something moves from here to there, what's really going on? In our model of physics, we start to have ways to really think about that. But there's this question of, do you take this object and just put it somewhere else in space? Is it the same object that is being sort of transported in what coordinates in space it's in? Somehow space is changing underneath it? Or is it somehow that you're recreating this object at a different point in space? These are kinds of questions that in the time of Greek philosophers, people thought about. In subsequent times, they sort of stopped thinking about those once there were mathematical formulations of these things. Now in our physics project, we really have to think about this again. But let me not divert in talking about how this works in our theory of fundamental physics. But let me ask the question, when Aristotle was trying to imagine how did motion work, what did he imagine? Well, for example, there's the question of why do things fall? Well, he said, because they have a preferred place in the world, and it's kind of in the down direction, so to speak. He didn't really have a notion of forces that cause things to move. He more had this idea that it just has a place it should be, and that's down, so to speak. Another thing that was an issue for Aristotle is if you push things, how do they move? In the time of Aristotle, most things you might push, you had to kind of keep pushing them to have them keep on moving. There was lots of friction in most kinds of systems that people were looking at the time. There was probably either a mixture of friction, or there were things like animals that were sort of moving themselves in ways that were yet completely different from the way that a sort of purely inanimate object might work. So that was in antiquity. And then I think there were kinds of questions like, how do you think about the process of things moving in space through time? Like we very routinely would make a kind of a plot that shows, oh, this is the position as a function of time. But that wasn't something that was familiar in antiquity. And so I think it was, what was it, Orem, Oresma, I don't know how it's pronounced. That was probably in the 1200s or something, that people started really having this idea that you could do the equivalent of sort of plot something as a function of time. But then it took until, the big use case for mechanics was things in the heavens, so to speak. Whatever might be going on Earth, it was clear that there was some inexorable motion that was happening in the heavens. You know, planets would move from here to there. The Babylonians certainly had sort of empirical models of how the planets moved that seemed to be quite mathematical in character. And there was sort of the question of, okay, so how did the motion of the heavens really work, of planets moving around and so on? And there are a variety of kinds of theories for that. And the theories tended to be more kind of explanatory theories. They were things like, you know, Ptolemy had this whole development of epicycles, where it's kind of like a whole elaborate kind of gear-like mechanism that was moving the planets around. And then Kepler sort of updated that to be more something where it was thinking about kind of platonic solids that were kind of more mathematical in character, that could kind of move on each other to reproduce the observed distances and motions of planets. And Kepler also observed these sort of empirical laws of motion that turned into Kepler's laws, that were things about you know, equal areas are swept out in equal times, and the 3/2 law for the relationship of the power law of the relationship between orbital period and distance from the sun, and so on. And so these were things that were known but were not really understood. It was like, okay, yes, I mean, Kepler had really wanted things to work out with all of these platonic solids sliding on each other in a very perfect kind of mathematical way, had actually observed these empirical laws about distances and periods of planets and so on. And then I think the very important moment in all of this was that Galileo, in probably the 1620s-ish, who kind of got interested in essentially mathematicizing things about motion. And in a sense, the mathematicization of things had, there were different kinds of things that have been mathematicized. Strangely, music was one of the more mathematicized kinds of areas, where people knew that the ratio frequencies of different notes that would correspond to being things that were in nice progressions, you know, the octave, factor of 2, the perfect fifth, a factor of 3/2, things like this. These numerical ratios were known, that was known since the Pythagoreans, actually, and one could kind of sort of physicalize those ratios by knowing that was the relative distance of strings that would be plucked, and the relative lengths of strings that would be plucked, and so on. But in any case, there was sort of the question of, could you mathematicize things about motion? And I think one of the important things that Galileo discovered was the quadratic law for the relationship between distance and acceleration. So this idea that you know, you drop something, how it goes, the velocity increases linearly with time, more or less, and the distance goes up like the square of the time. Now, again, Galileo would do things like, you know, famously drop 2 balls from the Tower of Pisa, which was at that time, well, I guess, the tallest building, other than maybe the pyramids and things, that was out and about in the world. But he dropped these balls and observed that, yes, it didn't matter what the balls were made of, they landed at the same time. Now, of course, that wouldn't really, that depended on all kinds of features of air resistance and so on. If he had actually done what I think a later astronaut did on the moon, of dropping, you know, a feather and a rock at the same time, and seeing that on the moon, where there's no atmosphere, they drop it with the same acceleration. Galileo wasn't really able to do that experiment, because air resistance would cause his feather to fall at a vastly different rate than his rock. But in any case, Galileo kind of observed this sort of mathematical relation between distance and time and so on, that was this quadratic law. I think Galileo was sort of motivated to define kind of universal laws of motion by the observation in 1608 moons of Jupiter, which kind of gave the idea that, well, yes, there might be sort of global laws of mechanics that might work out there in the satellites of Jupiter as they work in kind of the motion of the Earth, as they might work in terrestrial kinds of settings. But I think there remained all kinds of things that were not well explained, and notably the motion of comets was one that was not well explained. But I think the thing that began to happen with Galileo was this idea that things that were put in motion might stay in motion, and things and sort of an idea of what might be going on roughly with things falling, and was that really an Aristotle story, or was there something where there was something like a force that was making things fall? Newton really cleaned all of this stuff up in 1687 in his Mathematical Principles of Natural Philosophy book, and I think he was the one who really started to think about his laws of motion, for example, which said things like a thing not acted on by external forces will remain in its state of motion. Well, in other words, if you just sort of start something going, it will just keep going at the same velocity forever. And that will have been something completely unobvious to somebody like Aristotle, because it just wasn't an experience he had. He didn't have, an air hockey table. He didn't have these kinds of things where things would just stay in their state of motion. They would tend to come to rest through friction and things like that. And also Aristotle didn't have the idea of thinking of gravity as a force, like a force that you can make by pushing on things and so on. But by the time of Newton, he'd sort of unified the idea of force, the force of gravity, the force of you pushing on something, and so on. And his laws of motion, force equals mass times acceleration being second law, the important sort of law of motion, that was at some level a definition of the notion of force. And to say that is what force does, is it changes the acceleration, the state of motion of an object in just that way. Well, having figured that out, he then had to work out, how does this force idea relate to gravity? And that's when he came up with this universal law of gravitation, that the force of gravity is just the product of the masses divided by the square of the distance between two objects, and then tried to calculate things based on that force law for gravity. He didn't have force laws for other kinds of things. I mean, Hooke, for example, contemporary of Newton's, I don't think they got on particularly well, was the one responsible for example, the force law for springs, Hooke's law, that said that the force associated with a spring would be based on the extension of the spring. I have to say, I think it's said, I don't know if this is entirely true, that Newton had this comment, if I have seen far, it is because I have stood on the shoulders of giants. And I think the footnote to that was Hooke happened to be very short in stature, kind of what would be in those days called a dwarf. And Newton was kind of, it's said, kind of tweaking at Hooke by making that comment. Of course, that comment has become enshrined in things like modern patent law as the Otsog principle, on the shoulders of giants principle about when is there something really new in the world or not. But in any case, I think Newton, his sort of top sort of force law was his universal law of gravitation. Then the question was, okay, so we've got these laws of motion, we've got now this force law, at least for gravity. How do we actually work out how things move? Well, Newton, for example, tried to work out the motion of the moon, and he got the wrong answer. And it turns out that working out the sort of common motions of the sun, the earth, and the moon, that's a very difficult problem. It wasn't a problem that was really solved, really solved well enough to predict eclipses and things properly, wasn't really solved until about 100 years ago. And with even more precision, not until even more recently than that. But in the time of Newton, one of the questions was, okay, so we have these equations, we have these laws of motion. How do we then compute what's actually going to happen? And that became a great interest. And in particular, the problem, the three-body problem, particularly the Earth, Moon, Sun problem, became sort of a central problem of mathematical physics. Through the 1800s, for example, if you had asked people, what are you aspiring to do with mathematical physics? The answer would probably have been solve the three-body problem. So there were a lot of questions about how you would do that. But I would say there were a couple of other trends in the theory of mechanics. Another big trend was understanding rigid bodies. So understanding things like tops. Tops are very complicated, very messy to understand. And there was a whole tradition, I don't know, I particularly know the British tradition in this respect, of sort of the working out the motions of rigid bodies. Again, that was something that happened, I would say, particularly in the 1800s. And these things like the Pohlhodes and the Hürpelhodes and all these kinds of different axes that represented the possible the ways to parameterize the motion of a rigid body like a top. That was sort of another trend, was the whole rigid body mechanics business. Now, there were people who tried to streamline the treatment of mechanics. And I think the D'Alembert, Lagrange, these were people who were concerned with how do you take kind of the basic mathematical infrastructure that Newton had defined for mechanics, and how do you make that be something that is more streamlined and amenable to more effective calculation. I think the thing that that caused to be invented was sort of a mathematical structure of things like Lagrangians, which are a way of sort of generalizing this thing where Newton was working out sort of all of the different coordinates that had to be dealt with in a mechanical system, kind of each one separately, whereas in Lagrangians and later Hamiltonians, things like this, one was able to have a more streamlined approach to those kinds of things. Now, I would say that, again, a big motivation for all of this was celestial mechanics, the theory of the motion of planets. And there were a lot of different things that were developed for the sake of doing that. Things like Poisson's series. In a sense, what was being done was there were these equations. They were really hard to solve. I mean, Newton, for example, commented on thinking about kind of the motion of planets. He was sort of confused by their difficulty, and he made some comment about how you can in principle work out where the planets go, but he said working out the details of these motions exceeds, he said, if I'm not mistaken, the force of any human mind. In other words, God can move the planets as the planets move according to Newton's laws, but no human mind can work out how that motion will work. To me, that has a very interesting resonance with the idea of computational irreducibility that I've spent many years developing, this notion that even though you know the rules by which a system operates, it can still be sort of irreducibly hard to compute what the system will do. Now, computational irreducibility is framed in terms of our modern notions of computation, a little bit different from what Newton talked about, because Newton was dealing with continuous variables and real numbers and things, whereas now we have sort of a better way to parameterize sort of the amount of effort that needs to be spent on computation. And now that we think we understand something about how fundamental physics works, we know that that sort of effort of computation is the one that's being done by our universe, rather than this kind of idea that Newton had that there can be a precise position that can be of any number of digits of precision for things. But in any case, I think the sort of a motivating force in the development of mechanics through the 1800s was the idea of celestial mechanics, particularly the three-body problem. There were also things like the calculation of the motion of planets. So famously, Uranus had been discovered by Herschel with an actual telescope. Then Neptune was discovered by, well, Adams and Leverrier were the two people who were kind of the competitors for that discovery. But that was a discovery, a theoretical discovery. That was a discovery from looking at the perturbations to other planets and saying, let's calculate based on Newton's laws what else should be going on. Is there in fact another planet involved? And if you look at what Adams and Leverrier did, their work is this giant algebraic computation of what would the motion of planets be based on the position, based on there being another planet, and where would that other planet be? And eventually people looked for it and they found the planet in the position where it was predicted to be. It was a big sort of success of theoretical science, a big success of kind of the Newtonian paradigm. By the way, if you ask sort of what happened to the three-body problem, what happened was by about 1900, it was becoming clear that there was sort of a fundamental limitation on solving the three-body problem. I mean, there were things that were invented to understand the three-body problem. For example, Henri Poincaré invented topology to understand the possible solutions to the three-body problem, the sort of parameterization of the different possible solutions to the three-body problem. But it had become a little bit clearer that there could be sort of impossibility results. I mean, from Galois, from the 1830s or so, it emerged the idea that another thing people have been working on for a long time was you have a quadratic equation, there's a quadratic formula that was known to the Babylonians, you have a cubic equation that was discovered with great fanfare in, I guess, the 1400s by particularly around Cardano and people like that. That there was a formula for the cubic equation, there was a formula for the quartic equation discovered around the same time, but then would there be a formula for the quintic equation? Well, people worked on that for a long time, and then Galois, his work showed that no, at least if you wanted to represent it in terms of algebraic numbers, things like cube roots and fifth roots and so on, there wasn't a formula for the solution to a quintic equation in those terms. And so people got a little bit used to the idea that it might be impossible to compute something. And so when towards the end of the 1800s, it became clear that the three-body problem didn't have solutions, at least in terms of these kinds of algebraic expressions and so on. The official term, there were no algebraic constants of the motion other than the ones that were already obvious and known. That kind of killed off the notion that somebody was going to magically, quote, solve the three-body problem, and people kind of lost interest in that, and eventually it became clear you actually have to do actual computations to work out the motion of things, and these computations are pretty complicated. And when people started having to fly spacecraft and figure out exactly how should you navigate to the moon and things, it became quite important to know in more detail how to do these celestial mechanics computations. But that was sort of very much in the end going back to sort of the original equations of Newton, and a lot of the kind of the cool tricks for how one would solve particular equations in particular cases and particular kinds of series and so on. Increasingly that has become irrelevant, and it's really just to go back to the equations and solve them type story. And it matters a lot what the motion of outer planets and things has a surprisingly big effect on even things like the tides on Earth. They're affected by things like the motion of Jupiter and so on, and are hard to compute. But in terms of the history of mechanics, from a little bit longer ago, the other sort of strand of mechanics was the development of things like fluid mechanics and rigid body and solid mechanics. There's a notion of the question was, if you want to describe the motion of point particles, that's one thing. If you want to describe rigid bodies, that's another thing. If you want to describe the deformation of bodies under stress, how much strain, how much deformation is there when you put a certain stress on an object? How does that all work? That led to things like Young's modulus and other kinds of ideas in the area of solid mechanics and so on. Then there was the question of when things flow, things about fluid mechanics. And that led in the end to the Navier-Stokes equations, which were in the mid-1800s, I think. Those were partial differential equations. Kind of the development was, Newton invented calculus to deal with kind of understanding the effect of his laws, because basically when you work out the acceleration of something, you have to figure out, if you know the instantaneous acceleration of a thing, what consequence does that have for the position of the thing? And well, yes, it requires doing a couple of integrals, and that's what Newton had to figure out. And what his mechanics was really based on ordinary differential equations where you have specific discrete variables and you're looking at the dependence of their changes on each other. What came in more like the 1700s to 1800s was the idea of looking at things where partial differential equations, where you would have the rate of flow of a fluid at every possible position, and then knowing how the rate of flow of a fluid at every possible position affects its rate of flow at other positions. For example, Euler came up with the Euler equations, which are the sort of first level of description of fluid flow when one doesn't have to deal with viscosity, the kind of analog of friction in fluids. But so then this idea of dealing with partial differential equations, much more mathematically complicated. Even today, many aspects of partial differential equations really elude us in terms of the mathematics that they involve. But that was sort of a big necessary development to get to continuum mechanics, mechanics of solids, mechanics of fluids, things like that. And I think the sort of a part of that whole development was the introduction of the notion of fields. It was sort of a question of when you have a magnet and it will make iron filings line themselves up in a certain way, what's causing that? How do you think about that process? And I guess Michael Faraday, who was not really of a particularly mathematical turn of mind, was the one who really came up with this idea of, well, you can think about it as being a magnetic field, this thing that sort of defines this abstract notion of the effect of magnetism at every point in space. For example, it's an abstract thing which you can then see the effects of in the positions of iron filings and so on. Once this idea of fields had come in, one could kind of merge these notions that came from continuum mechanics and start thinking about these fields as things described by partial differential equations. You could say, what was the magnetic field at this point? What was the vector that represents the sort of magnetic effect at this point? And you could describe that as a field represented with partial differential equations. That whole process of doing that was originally very notationally messy and so on. That notation got significantly cleaned up by Maxwell James Clerk Maxwell in probably the 1880s or so. Eventually, he wrote a textbook about electrodynamics. He introduced Maxwell's equations, which are sort of vector analysis equations. Divergence of the electric field equals, is proportional to the charge density, things like this. And a thing he still had to deal with, sort of the individual components, the X component, the Y component, Z component. What really cleaned that up was the introduction of vectors, and then later sort of coordinate-free notation, but that had to wait until well into the 20th century to really get properly developed. But so the kind of overall, I would say, arc of development of mechanics, there was sort of from Newton, there was kind of this idea of forces as an abstract thing that you could think of as something that you could attribute motion to. Much later, the idea of fields as sort of the carriers of the source of forces and things. And then in terms of the sort of mathematical infrastructure, there was kind of the idea of you have these ordinary differential equations, later partial differential equations to represent continuum kinds of things. And then sort of the whole question of, well, given all these equations, how do you actually go ahead and solve them? And sort of a whole series of stacks of kind of mathematical infrastructure appropriate for solving those equations, and ways to essentially package features of the solutions of those equations and all the different components that were being represented in those equations, package them together in different ways. And that's at least a rough outline of history of mechanics, well, up until the 20th century. When we hit the 20th century, we start hitting things about relativity, general relativity, quantum mechanics, and then the advent of the use of computers in studying mechanical systems, which is sort of a separate story. I think I maybe left out one piece to this, which is statics. One of the things that was very big in the, particularly in the sort of post-industrial revolution, around that time was the development of a lot of mechanical structures. So it's like, how are you going to work out whether this bridge was going to hold up? How are you going to, like Gustav Eiffel, for example, with his his big demo of bridge building that was stuck upwards in the Eiffel Tower? How are you going to figure out that the Eiffel Tower wasn't going to fall down? Well, you had to do a bunch of static mechanical calculation. And so that was another branch of this whole business. There was the idea of dynamics, of the motion of things and differential equations and so on. And then there was statics, which was a story of sort of vectors of force and how those will be arranged, and a lot of kind of work, a lot of particularly French mathematicians involved in working out kind of the theory of how all that stuff works, and the how sort of forces, what turned into thinking about vectors, although that wasn't the way they were originally presented. So that was another sort of whole branch of mechanics. Later on, that sort of merged with dynamics as people started to think about, well, what happens when you deform the Eiffel Tower? There's one thing to figure out statically, how do you keep the Eiffel Tower from falling down? There's another, when the wind puts force on the Eiffel Tower and it changes as the gusts come through and so on, what effect does that have on the members of the Eiffel Tower? Okay, long answer to that. Well, let's see. Question here. Let me see. Down here. Okay. Okay. All sorts of questions here. All right. There's one from Ein here. Why was it the Europeans who created modern mathematics and not the Chinese? Chinese obviously had a head start. Why don't we use Chinese characters instead of the Latin alphabet? Oh boy. Well, it's a little hard to do these what if discussions of history, but I can say a few things. I think one of the things that really struck me as I tried to understand the history of mathematics is that various kinds of notational issues really slowed down the progress of mathematics. So, for example, Roman numerals, they are fine ways to represent individual numbers. You want to represent 14, it's xiv, etc. But one of the things that seems like it's a triviality is the things that are being used to represent numbers are letters. And that means that if you want to somehow introduce the idea of an unknown for an algebraic variable in an equation, it's like, how are you going to do that? You've got these letters and you've got other letters. Now, I should say that when Euclid was writing his elements of geometry, he did use letters to represent unknown things. He used letters to represent things like angles. But somehow when you wanted to combine those to make an algebra, to sort of combine the idea of actual concrete numbers with unknown things, that was really tough to do in the way that people had set up things like Roman numerals. By the way, Greek numerals worked the same way. I mean, in Greek times, the numbers were represented actually directly by letters of the alphabet. So, 1 was alpha, 2 was beta, 3 was gamma, and so on. I mean, I'm fond of telling a story about that, which is in Greek times, the successive numbers were represented by successive letters in their alphabet. problem was some letters went out of circulation. And so I forget what it is, maybe 60 or something is represented by a sampi, which is a character that kind of went out of circulation after the earlier period in Greece. But nevertheless, they had burnt in those characters as part of their numbering system. But I think one of the things that probably retarded the progress of algebra was this thing that you couldn't really distinguish kind of the numbers from things that were like what Euclid had referred to as unknowns, so to speak, what Euclid had used as unknowns, which were represented by letters. They all sort of got tangled together. When Hindu-Arabic numerals came to the West, which really happened from people like Leonardo Fibonacci in 1200 and 1210 or around that time, 1205, I think, was his Liber Abaci, the book of the abacus, that introduced kind of Hindu-Arabic numerals to the merchants in Italy and elsewhere. Once you had Hindu-Arabic numerals that were really different from letters, that got you to more start to be able to think about, oh, we can have a letter that stands for numbers and so on. And I think it was the development then of some of the notation for mathematics and starting 1400s, 1500s to 1600s that really allowed sort of the streamlined mathematical science to get going. You know, the multiplication sign that was invented by a person called William Outred, who also was the person who invented the slide rule. And various people like Leibniz commented, using the X for multiplication is really stupid. People will confuse that with an X written out as a letter. Of course, he was right about that, but nevertheless, the notation stuck. But I think in the question of why things developed in the West and not in China in terms of the development of mathematics, I don't know for sure. I think that there were some things that definitely came from China that were important parts of the story of mathematics. But well, let me talk about a few of the influences. So I think a lot of mathematics came out of ancient Babylon. Babylon, the Babylonian period was the time when, you know, cities were first getting going. People had to streamline a lot of kinds of things. They had to have much more organized ways to represent, I don't know, areas of land, weights and measures, things like that. That drove a lot of development of mathematics. And people like Pythagoras, no doubt, learnt things from ancient Babylon and probably spent time in ancient Babylon, probably Euclid as well. You know, a lot of that tradition of mathematics came from Babylon. And so there was one area where a lot of mathematics originated. One of the things that one sees is that the time scale for mathematics to diffuse around the world is comparatively short, possibly because particularly in those days, merchants were the ones who really were the main users of mathematics, and merchants traveled. And so, you know, if somebody knew about this kind of method for doing a calculation of interest, well, that merchant might be traveling off to some other country and would spread that information. And so you see kind of the diffusion of knowledge about mathematical kinds of things being comparatively rapid on the time scale of the sort of birth and death of civilizations. But there were a few things that we know, or very likely, came from sort of more Chinese traditions. So one of them was the invention of binary numbers, was probably something that came from the I Ching, where there's this these hexagrams that are basically the representation of binary numbers of different possibilities and so on. That was probably missionaries going to China probably learnt about that, and that's how, for example, Leibniz probably found out about the idea of binary in the mid to late 1600s. But I think the development of the big driver for a lot of that early mathematical development was merchants and commerce and so on. And I don't know exactly how that played out. You know, there were places where that was really in full swing, particularly around Venice and places like that, and so on, and later in London and so on. I don't know how that played out in other parts of the world, so I don't know whether that driver existed there for sort of mathematical development. In terms of, I think it's always an interesting question, what leads different kinds of development to happen in different parts of the world and completely not happen in other parts of the world. And sometimes there are surprisingly minor issues, like are your numbers distinct from your letters and so on, that are important, and that affect whether this particular thing happens to get discovered there or not. Then there are more cultural kinds of things, like is there anybody who's in a position to just sort of hang out and think about stuff? Or is there a reason is there a driver, whether it's commerce or military kinds of things, that's a driver for various kinds of technological development? And how does that play out in different kinds of cultures? So I think those are the things that seem to affect this. I mean, it is interesting that there are different kinds of development. For example, one that I was struck by recently is just a weird thing. The development of mathematical logic in the early 20th century. There's a whole bunch of people involved in this, and I've happened to have recently been researching a bunch of them. And a bunch of them, I thought, oh, that person's an American. I don't know anything more about them. It turns out there's this region in basically eastern Poland and western Ukraine. And in a first approximation, I would say solidly 2/3, and I haven't done this properly quantitatively, of the people who were involved in the sort of major developments of mathematical logic in the first part of the 20th century, solidly, probably 2/3 of those people were born in this fairly small sort of corridor in that part of the world. They didn't have any interaction with each other there. They didn't even go to school there in many cases. But it's a really strange thing that it seems like there's this sort of coincidence of people who got interested in this sort of formalization of mathematical logic who happen to come from that part of the world. I can't claim to explain this at all, but it's just an observation that I recently made. And I think one has to realize, if one looks in modern times at sort of what happens in different parts of the world, the movies get made in Hollywood, the cars used to get made in Detroit, but probably no longer. The tech stuff is sort of happening in Silicon Valley, and et cetera, et cetera, et cetera. There are these sort of regional concentrations of activity that develop in the world, and typically there are things that drive those about sort of the fact that it becomes a tradition in that area to do these kinds of things. And you go to Silicon Valley, and you'll go to your average Starbucks, and everybody will be talking about the latest startup that they're doing, and so on. In Hollywood, it's pitching a script, these kinds of things. It's these regional areas develop where there's sort of a lot of energy around a particular line of development. And I suspect that's a thing that one has seen in the history of science and mathematics as well. And different places got that or didn't get that. That's the best I can say. And it's sort of a comment on that. Yeah, a comment here that Pascal's triangle was known in China before Europe. Yeah, I think that's true. And I think that the Pascal's triangle is sort of closely related to all of these sort of combinatorial enumerations of things, which is the sort of the I Ching story. I mean, one has to be a little bit careful sometimes with these questions of such and such a thing was known in such and such a place really, really, really early. Because once you know it, it's kind of easy to go back and say, well, that thing was really sort of a sign of going in that direction or this direction. I mean, having been involved in a few things that have sort of turned into history of science myself, going back and saying, did one really understand this at that time? Well, I can say I didn't really understand it. going back, I can see that, yes, I actually did figure this thing out in some sense, but I didn't really understand the point of it at that time. I think that's a difficult thing projecting back in history. And it's true, for example, both with Indian and Chinese science, that the dating of things is often very difficult and not known within a course of many centuries. It's not known when important works were produced and so on. And so that creates difficulty in this. And this very fact that there's such rapid diffusion of knowledge around the world also confuses things. I mean, one of the examples of that I'm familiar with is there's a particular maze pattern that it's not clear where it originated. It's something you see on coins and things from the island of Crete. And so at different times, I think people said it was the logo of the city of Troy. It was a map of the labyrinth of the Minotaur on Crete. It was various kinds of things that had been designed. That labyrinth was designed by Daedalus, I guess, was one of the sort of mythical statements. And so this was the maze designed by Daedalus to sort of hide the Minotaur or whatever. And a variety of kind of mythology about this maze shows up. But what's interesting is this maze pattern, it's a very specific maze pattern, shows up all over the world, including in places like South America, including in by 1000 AD, it's on the floor of the cathedral at Chartres, things like this. It shows up very, very broadly. A very specific and arbitrary thing shows up very broadly, and that kind of gives you a sense of the diffusion rates of these sort of mathematical kinds of concepts. And so that's another thing that makes dating things difficult. Now, I think when it comes to questions, there are particular traditions that exist. So, for example, in Indian kind of mathematical tradition, there were things people cared about. Like one of the things that people cared about a lot was prosody, kind of the scanning of the sort of setting to music of words and the way that sort of the lengths of words scan and things like poetry. And there were questions that came up like, could you enumerate the possible forms of prosody and things? And so that presumably led to the development of Fibonacci numbers way, way before Fibonacci in India. And there were also things like, for example, there's a person called Panini who developed a grammar of Sanskrit. And that grammar of Sanskrit looked a lot like modern kind of production rules for representing sort of recursively representing grammars. By the way, here's a piece of history that I only learned yesterday. So I had been very confused about the origin of grammar, that of this idea of representing grammars recursively, saying you can say a sentence is composed of blah and blah, this phrase, this phrase, this phrase, and those phrases are in turn composed of this and this and this, and having these rules by which you can construct a grammar like that. Well, in 1956, two completely different traditions, or so they seemed, originated. One was the tradition of generative grammar from Noam Chomsky and so on, and the other was the tradition of what became called Backus-Naur form, so generative grammar was a way of describing human languages. Backus-Naur form was a way of describing computer languages, like things like Fortran and so on. And those two things both developed in 1956. And I had not understood how could this have happened? Were they independent? Were they connected? And so on. I asked Noam Chomsky once that question, and he didn't really give a definite answer to that. I didn't know, which came first. Did generative grammar come first? Did Backus-Naur form come first? Well, I was recently studying a person called Emil Post, who was a person who worked in mathematical logic, particularly well in several periods, around 1920, then around 1940. Emil Post invented these things he called production systems which were essentially string rewriting systems. And it turns out, I think both those traditions in 1956 came out of what Post had done in that he had originally done actually in 1920, but didn't really publish properly until about 1940. And then they sort of got ingested into textbooks around 1950. And I think that's where both of those traditions came from. They both came from Post's production systems. And that clears up a mystery for me, because it was very, very confusing to me that both would have originated then. Now, having said that they originated then, the idea for sort of recursively specified grammars appears to have been present in the work of Panini in, we don't know exactly when, maybe around a couple of centuries BC, a couple of centuries AD, I'm not sure, in India, working on the grammar of Sanskrit. So that's a case where there was sort of an origination, and I haven't really studied in tremendous detail what Panini did. It is my impression that it really was a sort of slam dunk example of, yes, there are these recursive specifications of grammars. I'm aware I had looked at one point about Latin grammars, notably Lucretius, for example, famously mentions in the 1st century AD, has this very nice statement that maybe the way that atoms form things in the world, he had the idea that atoms were the way that matter was built up, that atoms form things in the world much as grammar specifies that letters and words should be formed into sentences and so on, which was a very, very nice kind of way of thinking about formalism, but that kind of suggested that there was a very organized form of grammar in those times. And there were grammar books, but I don't think there was the same kind of recursive notion of constructing grammars that existed then. I think, let's see. Okay, the RBS mentions that math competitions might have been a thing. But I think not, because the really bizarre thing is that many of the people involved in mathematical logic, left at age 4 and things like this. So I think it's more, if anything, a cultural tradition than it is anything, for example, to do with education there. All right, I should wrap this up in a moment. I think maybe we've got, maybe I could try one more question. There's a question from D0 here. Let's see, there's a question of, there are obvious problems with peer-reviewed academic research. Is there a way that science was developed in the past that we can learn from, where we were better at sort of reviewing science? Well, it's a funny thing. If you look at the early scientific journals, so scientific journals, probably the first scientific journal was Proceedings of the Royal Society. People like Hooke were involved in that, and Halley was involved in that. This was in the late 1600s. If you look at the papers that people wrote in the Proceedings of the Royal Society, the early issues of it, they read very much like blog posts today. They're really kind of interesting and funny. They're things like, I went up this mountain at very early in the morning and it was very cold, and I observed this green flash when the sun came up. And meanwhile, the badgers were running around on the ground or whatever else. It's very much more telling a story. And the idea of the kind of desiccated scientific paper is something that's a much more recent origin. It also, even the notion that, what had been the case was that these kind of societies and journals and things were publishing more like blogs today, more like the narrative of what was going on. And there was pretty much, if you were a member of one of those societies, you got to publish in those journals, and you got to kind of have the things that you talked about there printed up and distributed to people. I think the notion of kind of scientific journals where you were just somebody out there in the world and you sent in your papers, I think those existed late 1700s, maybe early 1800s, but they were usually associated with a particular person. There was, like Krell's Journal of Mathematics, or sometimes with a particular place, a particular university. And it was like, you knew who was responsible. It wasn't kind of the faceless system. It was like, oh, I'm going to send it to so-and-so, and they're going to publish it. And I think that this idea, as science got bigger, the notion that it was all sort of a faceless process got more prevalent, and the idea that there wasn't sort of individual responsibility about, Mr. Krell or whatever being the one responsible for was that math paper published or not. The idea that it was sort of a collective decision that was done in a faceless way, that is the phenomenon of the upscaling of the size of science, pretty much associated with post-World War II period. I mean, what had happened, there were a lot of weird forces that were in play at that time. I mean, one of the weirder ones was this sort of publishing entrepreneurship in the wake of World War II, and particularly as things went into kind of the Sputnik era of sort of interest in, science being a really important thing. But even after World War II, it was clear that sort of science was a thing of greater national priority than people had imagined before, and so on. And so there was a drive to, let's build up sort of the science effort in different places at universities or elsewhere, different countries and so on. But one of the sort of entrepreneurial opportunities that created was there were all these random journals that had been published by, the journal of the lower such and such society of lower, of some small municipality somewhere, or this or that. There were a whole giant sort of patchwork of scientific journals, and entrepreneurs, particularly Robert Maxwell, was probably the most famous of these, kind of went around and sort of bought up these journals, and then went particularly to American universities and said, okay, I have the journal of the kind of I don't know, the Bratislava, mathematical weekly, whatever it was thing, I'm publishing this. Now you, as an American university library that wants to be having the best possibility of doing the best research, you must subscribe to this journal in order to be current. And so this idea of these giant number of journals, there was a big kind of commercial driver of let's have more and more and more journals, because by golly, these American universities particularly will pay for subscriptions to all of these journals. And so that became this vast industry that expanded the number of things that got published to the point, so that was one dynamic. The other dynamic that happened was the sort of the structure of the academic system, and the ideas about, tenure and the whole systematization of academic positions happened. That was, again, a post-World War II and then post-Sputnik kind of phenomenon. And that then needed kind of sort of ways to assess academics. And well, there was a chap called Gene Garfield. I knew him late in his life. He was the person who invented the Science Citation Index, which was, and his idea was to sort of understand the network of who cited who and be able to figure out, given that you found an interesting paper, who would be the people who were following up on that paper. And I used to use the paper versions of the Science Citation Index to figure out kind of what were the things, what were the future study of some particular thing that I found interesting. I did have the interesting experience in 1983. I was studying cellular automata, and they had many different names, but I'd found most of those names. And I looked up pretty much everybody who'd written a paper about these kinds of things ever. And I pretty much invited all the ones who were alive to a conference at Los Alamos. They never met each other. They didn't even know these other fields existed, partly because the names were different and so on. That was a lot of fun. But in any case, the sort of another driver was this idea of, your publish or perish type idea for academia, of just pump out more papers. Then there was the whole, I guess it's been in modern times actually, after I've stopped being an academic, that the whole, H index and citation, how do your papers fit into the citation network and so on, that's become important. But I think this ecosystem of lots of journals, university libraries had to have them, and then sort of the way of assessing academics, how many times did you publish? This led to this sort of giant system that becomes very faceless, very institutionalized. And I think that the earlier way of doing this, when science was much smaller, and it's like so-and-so was responsible for deciding to publish it. Okay, that person's an idiot. So that was a bad thing. But it was a particular person responsible. It wasn't sort of the faceless collective that was responsible. And I think that's, to my mind, the kind of the personal responsibility of and the sort of personal branding of sort of decisions about what gets to be published in the world, I think is something that was sort of a good feature of earlier periods of science. But science was much smaller. And one of the things that happens is when things are smaller, it's actually easier to be innovative. You might think when there are more people doing stuff, gosh, more ideas will come out. But that's one dynamic. But the other dynamic is when the thing is big and institutionalized, there are structures that say, well, it's got to flow in this direction. And if there's something that's not in the flow, we can't deal with that. So that it becomes actually more difficult for innovation to happen, even though there are more sort of potential sources of innovation. So I think those are probably the things. I think we're returning with sort of the blog posts of today are and my efforts to write about science, things I discover. I have not been writing. I haven't really written a pure academic paper since 1986, I think one of the things that is sort of a killer that happened in some areas of scientific paper writing is the kind of don't say why you're doing it. Just stick to the most official sort of facts you can. I mean, in mathematics papers, this becomes my version of this is the paper starts with let F be a field. And then it just goes blah, 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 blah. Why are we considering F? That is never mentioned. It's just let F be a field with these properties. And now we work out what consequences that has. That's very different from the style of kind of the narrative where you're explaining why are you doing this. And one of the things that's happened in a bunch of fields, mathematics being one of them, is that it becomes almost disreputable to say why you're doing it, to give the meta information about why you're doing something. It's like, no, just stick to the stuff that's the sort of formal things that happen in the field. The other dynamic that happens in more experimental fields, there's a great tendency to not tell the story. What happened to that mouse? Nobody's going to say this particular mouse stuck its nose in this thing, and so it didn't have a very happy time, and so when we tested this thing on it, that mouse didn't test out right. And instead, they're just going to say, the statistical significance of this is blah, with this number of mice doing this and that number of mice not doing this. There is no story behind that. Yet, if you actually knew the story of what had happened, it would probably give you a lot more information. It would also, to my mind, give you a lot more confidence in what was really done here. There's a lot that can be hidden behind the, statistical result XYZ. It's like, what actually happened? One thing that I've been doing, sort of an experiment recently in our physics project particularly, is it's a thing that's new and different and I think never been possible before. It's sort of the fully open science, where kind of I'm posting kind of the notebooks that I use every day. They get posted. Probably the things I did last night are already posted, of sort of the actual working notebooks that I've used to figure out the things I'm trying to figure out. And we've also been posting kind of videos of we've been live streaming some of our working sessions, and I've been posting videos. Some of them I think are perhaps a little bit weird to watch, but video work logs, I'm calling them, where it's literally I can record for 6 hours, completely silent. I'm just working on stuff. Now, is that useful? I'm not sure. The one thing I did realize is if somebody wants to know why is this number 3, not 2 in this document that I've written, in principle, you can really drill all the way down to see the moment where that number got written and, oh, maybe I was confused and it's wrong or whatever else. But you can really drill all the way down and see that. And that's a level of transparency that it's never really been possible before. It's something that I think is, I'm doing it as sort of an experiment. I think it's something one could argue would be a really good thing for sort of academics everywhere to think about doing, because it really gives you sort of the full story of, I want to know, much of the time you only want to know, tell me just the big conclusion. But if you want to drill down, you're really trying to understand what's going on, there's much more detail. Another thing, of course, of modern times is the whole computational language, computational essays, being able to take pieces of computational language. I'm routinely doing this. I've just been working on some stuff that I worked on last in 1991. The Wolfram language code that I wrote in 1991 still runs today, and I've been using a bunch of it. And that's a really nice thing to be able to have sort of a live, actionable, computational thing that you can pick up many years later and use. I think that's another feature of modern times that didn't really exist in the past. But I think perhaps the closest analog, it's not necessarily my favorite, but used to be the case that surgical operations were sometimes done in operating theaters, which were literally a place where people could watch the operation being done. And that was, I don't think that's my favorite analogy, particularly being a squeamish person that I am, for my kind of open working session approach to science. And I think that that's but that's sort of this there were some other things actually of ancient times, or a while ago, about the way science was done. I mean, there were strange kinds of public events, like the presentation of the solution to the cubic equation. That was a whole sort of bizarre, skullduggery included public event, and that's something that and there were sort of public competitions about ideas and things, which are a little different from what we see today. I mean, I would say that there was there an analog of kind of science announced by Twitter? I don't know. I think that's probably not so much. I mean, there were the societies in London and Paris and places like that were publishing their weekly sort of discussions, and so that was the thing that was happening on a pretty short timescale there. I think, and there was a lot of science that was conducted in correspondence between different kinds of people that was very email-like. I mean, by the time I know when I was studying the history of Charles Babbage and Ada Lovelace in London in the 1840s and so on, there were like 14 mail deliveries per day in London at that time. So that's a pretty good approximation to kind of email rates of exchange of ideas. So those are a few thoughts. But I think that the notion of the sort of anonymous jury of peers, peer review idea is a comparatively recent notion. And I think it is one of the probably downsides of the kind of giant institutionalization of science. Yes, we can probably learn from earlier periods the more personalized approach to sort of taking responsibility for what's said in science. I tend to much prefer. All right, I think we should probably wrap up here. I see a lot of other interesting questions, which I look forward to addressing another time. So thanks for joining us here. And our schedule is in 2 weeks. At this time, we'll do another History of Science and Technology Q&A. And 1 week at this time, we'll be doing a Business and Innovation Q&A, although we're thinking of moving that to possibly to a slightly different platform, and that might change. I am back to my day job in a minute here, and I'm actually going to be live streaming a design review of some Wolfram language functionality in a few minutes. Well, thanks for joining.